Okay, so now we're going to consider a second very special but very important example of collisions in one dimension. So remember, last time we had derived conservation of energy and conservation of momentum equations in one dimension. These first two equations, 1 and 2, are always true, regardless of what kind of collision you have. And so you'll notice that the conservation of momentum equation is one equation in the two unknowns, the two final velocities, little v and big V prime. And the second equation is also an equation that involves the two unknown final velocities, v and v prime, in this term over here. Okay, but then the wild card is this term, delta E other. And so while these two equations are always true, we can't solve them until we say something more about the nature of the collision. And so we talked already about perfectly inelastic collisions and how we can use that condition where delta E other is equal to 0 to solve these two equations. Now we're going to talk about perfectly inelastic collisions. And so in this case, the idea is this is a hit and stick kind of collision. Okay, so we've got one object moving slowly to the right, one moving fast to the right. They come together like this. They hit and they stick. And together they move off with the same final velocity. So little v and big V prime are equal to each other. Okay, so then you can say, yes, well now I have this third equation is an equation in the two unknown final velocities. The first equation is an equation in the two unknown final velocities. That's two equations and two unknowns. I can solve those for the final velocities, little v and big V prime, and then I can stick them into this term in the second equation, and I can calculate what delta E other is. How much of the original kinetic energy in that hit and stick collision went into other forms of energy, like thermal, like deformation energy, like sound energy, and that kind of stuff. Okay, so this is a very important class of collisions. So let's just draw a picture just to sort of orient our minds as to what's happening here. So we've got one object of mass little m, which is, say, moving to the right. So its velocity, which can be positive or negative, in this case is positive. And we have a second object of mass big M, and suppose that it is moving to the left, and we're going to have a collision like this. So its initial velocity, big V, it's a variable that can be positive or negative, is negative in this particular drawing. Okay, so then these two objects, they come together and they collide. And so then they collide at this point. And when they collide, they don't necessarily, they'll hit and stick, but they will not necessarily be at rest after sticking together. So if this one has a lot of momentum to the right, more than this one has momentum to the left, then after they hit and stick, the two of them will together be moving off to the right. Okay, so let's suppose that's the case. Depends on the situation, of course. It depends on which one has more momentum. Okay, so then in the aftermath of the collision, these guys sort of are hit and stick. So we have an object of total mass, little m plus big M, which is moving to the right with a speed. So the final velocity of little m, little v prime, is equal to the final velocity of big M, big V prime. Okay, so that's that. And then the interesting thing is that some of the original kinetic energy in the problem will be converted to other forms of energy. And so usually we think of this as thermal energy. Okay, so like two blobs of clay, when you throw them at each other and you measure the temperature of that clay afterwards of this blob, it'll have warmed up. So there's been an increase in thermal energy. Okay, so this, well, how should I put this? Delta E other. Yeah, okay, let's put it here. Delta E other can take various forms. So it can be a change in thermal energy, so the objects heat up. It can be a change in the sound energy, an increase in the sound energy. It can be delta E deformation. Suppose it's a car crash and then metal stores energy and so on. So these little lines radiating out indicate increased warmth, sound coming out, or whatever, that kind of stuff. But of course, total energy, or energy, is always conserved. So the total energy in this isolated system will always remain the same. Okay, great. So now let's solve equation, I guess equation 1 here. Okay, so equation 1 is conservation of momentum. And if we know that the final velocities of both of them are the same, we can plug that into equation 1, and then we can solve for what that final velocity is. So that's very easy to do. So equation 1 we'll focus on first, which is conservation of momentum. So what does equation 1 tell us? Well, I mean, we can use this form directly, or we can just use common sense and say, well, what it's saying is that the total initial momentum in the system, which is what? We've got an object of mass little m moving with a velocity v plus or minus, and an object of mass big M moving with initial velocity capital V plus or minus. That's the total initial momentum in the system. Well, that's equal to the total final momentum in the system. The total final momentum in the system is we have an object of mass little m plus big M here, which is moving with the common velocity little v prime or big V prime. So let's put little v prime there. Okay? So immediately we can read off from here that little v prime is the total initial momentum divided by the sum of the two masses. So that tells us that little v prime, which of course is equal to big V prime, both objects have hit and stuck together and are moving with the same final velocity. And what's that equal to? Well, it's equal to the total initial momentum in the system divided by the sum of the masses, the total mass in the system. Okay? And my pen is running out. Let me grab another one. Okay, so now this result here, P total initial, so this final velocity of this stuck together blob of masses can be to the right, so the total momentum to the right, or it can be to the left, total momentum to the left. That just depends upon what the total momentum in the system was to begin with. So if this object had more momentum to the right than this object, say, had to the left, then the total momentum in the system was to the right, and so little v and big V prime are to the right. So you can see that this, how do I want to write this? This can be positive, 0, or negative according to the sign of P total initial. So P total initial is positive, 0, or negative. Okay, so that's kind of obvious. But what's interesting is this case over here. This is the interesting case, which we're going to focus a considerable amount of attention on, is when the total momentum in the system originally, and of course finally, is equal to 0. So that when they hit together, hit and stick, they remain at rest, or they end up being at rest. So the total momentum final is 0, as was the total momentum initial. Okay, so that'll be an important special case that we're going to focus some attention on. Okay, so that's conservation of momentum. Immediately tells us, if it's hit and stick, immediately tells us what that final velocity is. And you can see P total initial, if I take little m plus big M and multiply by the final velocity, well, the final momentum is equal to little m plus big M times the final momentum is little m plus big M times that final velocity. So this equation simply says P total initial is equal to P total final. Okay, so that's easy. But now the more interesting equation is equation number 2. Now that we know what the final velocities are, we can plug them into this term and calculate delta E other. Okay, and then it gets interesting. So now we're going to focus our attention on equation number 2. Okay, so let's see. So in equation number 2, we have to figure out these two terms. This one, little v average minus big V average, and delta little p. Okay, so let's work on that. This will take just a minute of simple calculation. So the first thing is we want to figure out what is the difference in those average velocities. So little v average minus big V average. So what is that? So average velocity is initial plus final divided by 2. So 1/2 the initial velocity of little m plus the final velocity of little m, and then we subtract 1/2 the initial velocity of big M plus the final velocity of big M. Okay? But then our hit and stick condition is that those two final velocities are equal to each other. So here we have a positive little v prime, there's a negative little big V prime. So those things cancel out. And so what we get is, can I fit it here? What we get is 1/2 little v minus big V. Okay, so that's an important result. So now we know what this term is. Now we need to work on delta little p. So what's that? So delta little p is a little trickier. Let me give myself a little bit more room here. Okay, so so first of all, delta little p, that's what we're trying to calculate. So what is delta little p? That's the change in momentum of little m, final minus initial. So that's going to be little m times the final velocity of little m minus the initial velocity of little m. Okay, so we have that. And let's compare that with the change in momentum of big M, which we called delta capital P. Okay, so that's going to be big M times big V prime minus big V. Okay, now the condition that we have is, this is what we're trying to solve for, delta little p. The condition that we have is that the final velocities little v and big V prime are equal to each other. So these two things are equal to each other. So whenever you see that in two equations, you can use that to, roughly speaking, subtract these two equations and cancel those two terms out. But unfortunately, there's a little m in front of here and there's a big M in front of there. So what we do is we multiply this whole first equation by big M, and multiply this whole second equation by little m, and then subtract. Okay, so let's write that out. We're going to multiply the whole first equation by, so what does this tell us? Multiply the whole first equation by big M. So on the left we get big M delta little p, and then we're going to subtract this whole equation multiplied by little m. So that's little m times delta big P. So big M times this equation, little m times this equation, and then subtract. So the left-hand sides are big M delta little p minus little m delta big P. On the right-hand side, we have a big M little m v prime, little v prime. In the second equation, we have a little m big V prime. When we subtract, that and that cancel out. And so what we're left with is little m big M times negative v, subtract big M little m times negative v. Okay, and so that's the same as negative little m big M times little v minus big V. Okay, so it looks like that. And so we're almost done. What we're trying to solve for is delta little p. But we remember, basic idea of momentum conservation is that the change in momentum of little m is equal to the change in momentum of big M with a minus sign. So the change in the total momentum is 0. So this delta big P right here that we see is the same as negative delta little p. So the left-hand side has a common factor delta little p, and it's a negative, so it's a positive little m plus big M times delta little p, that's the left-hand side, is equal to the right-hand side that we just calculated. Okay, and so we get a final result here. I guess I'll put it here. So, therefore, solving for delta little p here, delta little p is equal to, there's a minus little m big M times little v minus big V, and then divide the whole thing by the sum of the masses, little m plus big M. Okay, so now we have, we're trying to calculate delta E other. We have just calculated the difference of the average velocities. That's this thing. And we have just calculated delta little p. That's this thing. Okay? So then we can write down, we can say, well, that means that negative delta little p times little v average minus big V average. Okay, so that's this thing with a minus sign stuck in front of it. What is that? Well, it's negative delta little p, so negative is a positive, so there's a positive here, and there's a little m big M divided by little m plus big M times little v minus big V, okay? And then we need to multiply by the difference of the average velocities, which is 1/2 little v minus big V. So there's a half, another factor of little v minus big V makes that little v minus big V squared, okay? If we take this object to the left-hand side, we get a negative delta p times the difference in velocities is equal to delta E other. Okay, so now this is a very important and interesting result. Very, very general and powerful. Okay, so let's, so you can see clearly this is a mass squared divided by a mass. This has the dimensions of mass. It's like 1/2 a mass times a difference in velocity squared. Now, as you get more advanced in physics, say in second year Phys 263, you will recognize immediately that this quantity over here is called the reduced mass. And the reduced mass satisfies this relationship. 1 over the reduced mass is equal to 1 over one of the masses plus 1 over the other mass. It's a little bit like adding resistors in parallel. And so it turns out that in 263 you'll learn that any two-body problem can be converted into an equivalent one-body problem, where the mass of the one body involved is this thing called the reduced mass. Okay? And then what appears here is the relative velocity between those two. Okay, so yeah, little v minus big V, the relative velocity squared. So this is clearly a kind of kinetic energy. It's a 1/2 reduced mass times relative velocity squared. Okay, so this, if you knew a little bit of more physics, this idea of reduced mass, you could have guessed this formula instantly. Okay, and we're going to elaborate on that a little bit more because that's a very, very powerful and general result. Okay, but before we do that, let's just do sort of a super simple example just to fix ideas in our head. So we'll take the simplest possible example of this situation is we have two objects of equal mass coming towards each other with equal but opposite velocities. Okay, so the super simple situation, or the simplest situation, is we have little m moving to the right with a velocity, say, positive velocity little v, and we have big M equal to little m, and big V equal to negative little v. Okay, so we got that situation. Obviously, the initial momentum is equal to 0, and when they hit and stick, they're going to look like this. They're going to have deformed and whatever, and so they're going to be at rest, first of all. Okay, but then some of that kinetic energy in that system will have been converted into other forms of energy, which are like, thermal deformation, all that other stuff. So we sort of indicate it that way. This thing is, say, a hot object now, okay, sitting there at rest. Okay, so let's just double check. Let's look at P, what do we have here? P total initial. So P total initial. So P total initial is, we have an object of mass m moving with velocity v, and we add to that an object of mass m moving with velocity negative v, so that's obviously equal to 0. And so what that tells us is that the final velocities, we're just sort of doing this kind of formally, and for completeness, this is sort of obvious. The final velocities are obviously 0, which is what one of our equations back here said. If P total initial is equal to 0, well then the final velocities are equal to 0, and the thing ends up at rest. Okay, so that one's obvious. But the interesting one is this. Delta E other in this case is equal to 1/2 little m times big M is little m times little m, because big M is equal to little m. And then in the denominator, we have a little m plus a little m. And here we have, and it's important to get the signs right here, it's little v minus big V. And big V is negative little v. So it's minus negative v. And then we square that whole thing. Okay? And I'll let you work out the algebra for that. That's trivial. So that turns out to equal twice 1/2 mv squared. And so 1/2 mv squared is the kinetic energy of this. Twice 1/2 mv squared is the original total kinetic energy in that system. And you will see that all of that kinetic energy has disappeared, and it has gone into typically thermal or whatever. Let's suppose it's basically thermal energy. I want you to sort of, let me just write this down first. So what it's saying is that all of the original kinetic energy, K initial, was transformed by force. I mean, you have, when these two objects collide, there are forces acting, and these objects are deforming like this. Force acting through displacement. That's work being done. Energy is being transferred. It's being transferred from kinetic energy into, let's say, thermal energy, predominantly. Okay? So delta E other, more generally speaking. Okay, through the process of work. So, in most cases, it's mostly delta E thermal. So there's an interesting fact about this, or an interesting way to think about this. The original kinetic energy in the system is highly ordered in the sense that all of the particles are moving with the same velocity. And then they hit and stick together like this and deform. All of that kinetic energy is still there. Those particles are just jiggling around more vigorously now. And so that nice ordered kinetic energy has become disordered kinetic energy. Well, disordered kinetic plus potential because it's a solid. So there are, interatomic bonds, and so they're like little springs. There's energy also stored in little springs. Okay, but basically, ordered energy has become disordered energy. So this is a very interesting sort of thermodynamic process as well, which increases the entropy of the universe and all that kind of stuff. Anyway, so that's that. So that's cool. But now let me say something that's the most interesting and the most general. So in this particular case, we obviously had these guys are totally symmetric, and we obviously had that these guys are going to hit and stick and end up at rest. But the fact of the matter is, given any situation, say like this general situation here, you can always move to a frame of reference in which the total initial momentum of the system is equal to 0. And you're going to end up with these two masses, when they hit and stick, they will end up at rest. Okay, and that's a very, very important case to consider. So I'm just going to erase the board, and I'll come back and tell you a little bit about that. Okay, so this is a very important concept in physics in general. The idea is that in any collision, one-dimensional or otherwise, you can always move to an inertial reference frame in which the total momentum in the system is equal to 0. Okay, so this is called the center of momentum frame, or the zero momentum frame. This is a very important concept, especially in particle physics collisions and stuff like that. It leads to this idea of available energy, which is really this thing. Okay, so that's what I want to get to. It's a very important general concept that everyone should know about, physics students should know about. Okay, so let's imagine, just to sort of fix ideas here again, that we've got an object of mass little m. Let's say it's moving to the right with a speed v, relatively fast, and then it's chasing after an object of mass big M moving to the right slower, like that. Okay, so obviously the total momentum in this system initially is, or originally in this original system, is to the right. Okay, so now what we're going to do is we're going to put ourselves in a reference frame that's drifting to the right like this, such that in that new reference frame we will see a total momentum that's actually equal to 0. Okay, so we will consider this person over here, and this person is in a reference frame which is drifting to the right relative to us. It has a velocity that is bigger than big V, but smaller than little v. It's sort of in between. Okay, and we'll call that velocity u. Okay, and then the question is, what does this person see? How does this person view this situation? Well, if this mass were at rest, say, and this guy's drifting to the right, then this guy will see that mass moving to the left. So basically, and similarly for this guy, so basically what we need to do to transform from this picture that we see in the original inertial reference frame to what this guy sees, we just need to subtract u from both of those velocities. Okay, so what this guy sees is this. So let's put it like this. In his frame of reference, what he sees is an object of mass little m moving to the right with a speed that is this velocity v minus u. We just subtract u from both of these velocities. Okay, so that makes little v shorter, but it's still going to the right. And we have an object of mass big M moving with a velocity big V minus little u. So big V is short, subtract a larger velocity to the right, we'll get a velocity to the left. So now they're both doing this sort of thing, and if we choose this velocity, this relative velocity u, properly, then we can adjust u so that the total momentum in the system is 0. Okay, and so what will happen then is exactly like this. They will hit and stick, and when they stick, they end up at rest. So they hit and stick like this, but their final velocity is equal to 0 because the momentum originally in the system is 0, so the momentum finally in this is total momentum initially is 0, so the total momentum finally has to be 0, and so they are at rest. Okay, so but maybe they've heated up, increase in thermal energy, that kind of thing. Okay, so this is called the center of momentum frame. Okay, so good. So how do we figure out this, this relative velocity u so that the total momentum is equal to 0? Well, what we need is this. We need 0 equal p total in this center of momentum frame. Okay, so what is the total momentum in this frame? Well, the total momentum is we have an object of mass little m moving with a velocity little v minus u, and then we add to that the momentum of an object of mass big M moving with a velocity big V minus u. So big V minus u is a negative quantity in this case, okay? So we have that. So what is that? Well, if you look at this term, this is m little v, this term is plus big M big V. Well, that's the total momentum in the original system, okay? That's little m v, little v, big M big V. Okay, and so that's equal to P total in the original system. Okay, and then what's left over is a negative u times m and a negative u times big M. And so there's a negative u times little m plus big M. Okay, so then all of this has to add up to 0. And so we can solve for little u. So little u is the total original momentum divided by the total mass in the system. Okay, so that tells us that the relative velocity, the velocity we need to drift at relative to the original setup there, is we just take the total of momentum in the system in the original system here, in the original inertial reference frame, and we divide by the total mass. So momentum divided by a mass is a velocity. Okay, so that's an important result. Okay, and what else? Oh, so now here's the important point. Okay, so when we change our frame of reference, we change the kinetic energy that's present in the system. Remember that kinetic energy is a relative concept. So here is an object, and it has 0 kinetic energy relative to me. But if I'm in a frame that's drifting toward it, well, then it has kinetic energy. Okay, and so the kinetic energy in the system depends upon your choice of inertial reference frame. For example, suppose we have both of these objects moving to the right. Well, maybe one faster than the other, but they're basically moving to the right like this. There's certainly some kinetic energy. If I were to go in a reference frame that's moving to the left like this, well then in that new reference frame, those two objects are moving faster to the right, and obviously they have more kinetic energy. So it should be intuitively obvious that I can adjust my inertial, the velocity, the relative velocity of this moving frame here so that I can minimize the amount of kinetic energy in the system. Because if you go super fast this way, well, there's tons of kinetic energy. If you go super fast this way, there's tons of kinetic energy. So there must be some choice of relative velocity u that will minimize the kinetic energy. And it should be intuitively obvious that it's this frame, the center of momentum frame. Okay, so I'll just write that down. So this is an important statement. So the kinetic energy total, the total kinetic energy in the system, sum of the kinetic energies of the two masses in motion here, certainly depends on the choice of inertial reference frame. Okay, and it is minimum in the center of momentum frame. Okay, so this is the center of momentum frame. We figured out what u needs to be. So let's calculate what that minimum total kinetic energy is in this center of momentum frame. Okay, so in this center of momentum frame, so this calculation, there's a couple of lines in this calculation, no big deal. Good exercise in algebra. Okay, so kinetic energy, the total kinetic energy in this situation over here, originally, right, because afterwards the rest is no kinetic energy. We're talking about the initial kinetic energy total in the center of momentum frame. So what is that? Well, we have an object of mass little m moving with a velocity little v minus little u squared, plus we have an object of mass big M moving with a velocity big V minus little u squared. Okay, so somehow we have to simplify this thing. Okay, so there's two major steps in that simplification. So the first step, I wonder if I can fit this here. Yeah, I'm going to erase this, and then I can fit it here. Okay, so this is equal to, so always whenever you're doing calculations like collision calculations that have squares, always try to separate those squares out. Like a squared minus b squared is a minus b times a plus b. We've used that trick before. Here we're going to just separate out that square. We're going to write it as 1/2 little m times little v minus u times little v minus u. And do the same thing here. Plus 1/2 big M times big V minus u times big V minus u. Okay? And so the reason you do that is now you have terms that are linear in like mass times velocity, mass times velocity. And those look like momentum type things, okay? So let's look at that. So we're going to focus on this little m times little v minus u, and focus on this big M times big V minus u. Now where do we see that before? Well, big M times big V minus u, that's this thing over here. What is that? Well, according to the condition that the total momentum in the center of momentum frame is equal to 0, it says that this thing is equal to the negative of this thing. Ah, but what's this thing? Well, that's that thing. Okay, so these two terms are equal except for a minus sign. Okay, and so that's an important first step in all of this. So we can write this as, so there's a common factor, 1/2 little m times little v minus u. Okay, that's that factor, times, from here we have a little v minus a little u, but big M times big V minus u is the negative of this thing. So it's just the, common factor is this, and so then we just subtract this term. So there's a negative big V and a positive little v. Negative big V, positive little u. Okay, and so delightfully the u's cancel out. Okay, so now we have something that's getting close to the end. This is just little v minus big V. That's great. But now we have still this u inside here. So how do we deal with that? So let's, I guess, start erasing a little bit over here. We're going to need a little bit more room. We'll try to leave up this. These are all just calculations, intermediate calculations. We'll try to keep up the final results. Okay, so what we need now is we need an expression for little v minus little u. So little v minus little u, what is that? Well, it's little v minus u. Well, we calculated the required relative velocity of the inertial reference frame to make the total momentum equal to 0, and little u is equal to this thing. So let's plug that in there. So this is the total momentum in the original system, which is little m, little v, plus big M, big V, divided by the sum of the masses. Okay, and so now this is a trivial exercise for you to work out. Take a common denominator of little m plus big M and simplify that expression. And so what you get is big M times little v minus big V divided by the sum of the masses when you take little m plus big M as a common denominator. Okay, so that's nice. So now we can plug that into here. In fact, let's just do that. Well, how much room do we really need? Let's do it right here. Okay, so then what we get is K total, the total kinetic energy originally in this center of momentum system. Okay, so what is that? That's equal to, let's just sort of do this all in one step here. There's a, well, we want to, this over here is little v minus big V. This is also little v minus big V, so we'll have that squared. So there's a 1/2, first of all. Then there's a little m. And then we need to multiply by little v minus u. Little v minus u is this thing. So there's a big M. And then there's a divide by little m plus big M. And then there's a factor of little v minus big V. And then there's a second factor of little v minus big V squared. It's a 1/2 mv squared. That's a kinetic energy. Okay? So we get that. So that's a really nice and powerful result, and you see that it's identical to the other result that we had, okay? So what's happening is if you start in a frame of reference where the total momentum is not initially zero, you'll have this hit and stick collision, and some of the kinetic energy will be converted into other forms of energy. Whereas if you move to the center of mass frame, then all of the original kinetic energy goes into other forms of energy. So K total in the center of momentum frame initially, which is the initial kinetic energy, all goes into this delta E other. Okay, so because remember that if you have a situation where you start off with a non-zero initial momentum, then this hit and stick thing still has kinetic energy in it. Okay. So anyway, so that's a very important sort of thing. So let me now erase this because we've seen that now it's the same. We've gotten the same result from sort of a much more general sort of point of view. Let's talk about that, because this is a very important concept whenever you do particle physics. And we know that sort of huge amount of physics. You know, half of what we know fundamentally about physics is the Standard Model of particle physics. And so this is very important when you're doing particle physics calculations. Very important concept for physicists to generally know. Okay, so this is called the available energy. Okay, that's an important term. And so it's the energy that's available to be converted into other forms of energy. Okay? Because basically, you've started with some kinetic energy in the system. At the end, you have no kinetic energy. Well, energy is conserved. So all of that kinetic energy has gone into some other form of energy. And so the other forms of energy, so this is, what does it mean? It means available, it's energy available to create or generate other forms of energy. So for example, thermal energy, two objects stick together, they heat up. The usual example is sound, when billiard balls, click together or whatever. Well, here's a hit and stick, okay? Collision, so it's not elastic like that. And then, deformation, cars hit and stick together and metal is bent and so on and so forth. But it's much more general than that. So there's also, this is the most interesting example, and new particles. Okay, so for instance, you can start, so basically kinetic energy is converted into rest mass energy. Okay, so what does that mean? So a typical example, the simplest possible example is we have two run out of room here. Anyways, okay, let's do it like this. So we have two low mass particles moving fast. Okay, lots of kinetic energy, and they come and they undergo some kind of collision process. Okay, they undergo some kind of interaction, and it can happen in that interaction. The simplest imaginable thing is what goes in is two light, fast-moving particles, lots of kinetic energy, and what comes out is two slow, more massive particles, either at rest or moving very slowly. Okay, so we have generated rest mass. Okay, so kinetic energy has been converted into rest mass. Okay, so here is the point of the collision. So let me just sort of write it out. So two light particles say low rest mass particles that are moving fast. They have kinetic energy, and this can be converted into say particles with heavier rest mass, and we're saying a pair so that we have zero momentum initially, zero momentum finally from the symmetry. Okay, we have to conserve momentum and of course energy, and then some of that kinetic energy gets converted into can get converted into rest mass energy, and you can create heavier particles. So converted into two heavy slow particles, or two heavier particles at rest, whatever, such that the total kinetic energy in the final is less than the total kinetic energy to begin with. Okay, so then kinetic energy has decreased. Where has it gone? Well, it's gone into increased rest mass energy present in the system. Okay, and so one final thing to say here, just sort of as an aside here, is to do with all of this, because this is a relativistic situation, and quantum relativistic situation. But let's think about a relativistic situation, a simple classical relativistic situation. So what we have is a frictionless surface, and sliding on this frictionless surface are two equal mass objects. Their rest mass is little m. So when they're at rest and you pick them up and shake them around, they present a certain resistance to changes in the motion, and that's their rest mass, little m. But we suppose that these things are moving fast toward each other to have a hit and stick collision. So then the energy in the system, to begin with, the total energy in the system, well, the energy is equal to gamma mc squared. So when it's at rest, it's just mc squared. When it's in motion, there's an extra factor of gamma. And that gamma makes it bigger than mc squared, and the amount by which it's bigger than mc squared is the kinetic energy of motion. So E for each of them is gamma mc squared, so the total energy in this system is twice gamma mc squared. Okay, so that's great. And remember that these two systems, we can put a box around this whole thing. In fact, let's just do that. Let's just put a box around the whole thing, and imagine we have a box containing these two objects sliding towards each other like this. If we were to try to pick up that box, if we were to try to accelerate in this direction, we would say, this box presents a certain resistance to changes in its motion. So we apply a force, say in this direction, and we measure the inertia of this system of two moving masses like this. And what we will find is that the mass, well, let me do it this way. Let's say that the mass of this system of two objects moving together like that, how do we calculate that? How do we measure that? Well, the mass, the inertia of this thing is equal to the force that we apply divided by the acceleration upwards that we observe. Okay? Suppose we did that experiment. What we would find is that that mass, that resistance to changes of this motion of that box from rest to some velocity, is going to equal the total energy in the system, 2 gamma mc squared, divided by c squared. Because for a system at rest, the energy E is equal to mc squared, where m is the rest mass energy. And so this box is at rest. It contains things in motion, but the total momentum of all the stuff inside the box is 0. Okay? And so what is this? Well, E divided by c squared, well, that's 2 gamma m. So it's gamma times 2m. So the important point here is that the inertia of this pair of masses in motion is greater than just 2m. So it's greater than 2m. So that's the important thing. Okay, so now we let these things collide and come together, or come together and collide, hit and stick. So now the situation looks like this. It's the same box. Okay, but inside we've got these two masses, and they have hit and stuck together, and they've heated up, basically. Okay, and so remember that the total energy is the same. Energy is a conserved quantity. The total energy is the same. Okay, and the total mass, if you were to do this experiment again after they've hit and stuck together, and you now have a hot object which has, I shouldn't put the m's in there. anyways, we have this object. And if you were to try to accelerate that box up and do that calculation, you would get the same mass m, same resistance to changes in motion. Okay, because no energy has entered or left the box, the energy has to be the same, energy conservation. And for a system at rest, the inertial mass is the energy in the box divided by c squared. And so what's happened here, interestingly enough, is where should I write this? So it's the same, is the points, the same energy and the same rest mass, inertial mass for that box, as in this situation, okay? And that mass is greater than 2m. So the extra mass, this extra mass that was in this system, instead of just being 2m, it's gamma times 2m. So that larger mass, the extra mass, is it starts out being in kinetic energy. So these are two rest masses m in motion. So there's some kinetic energy in the system, and that kinetic energy contributes to a greater inertial mass for that box. Okay, so that extra mass was originally in kinetic energy, and then in this case, it got transformed into, let's say, thermal energy. Okay, so now you have two objects with rest mass m that are stuck together, but the mass isn't 2m because the object is now hotter. There's more thermal energy, and that thermal energy also has inertia. Okay, and so the extra mass is now in thermal energy. Here the extra mass is thermal, here the extra mass is kinetic. There's been a conversion of kinetic into thermal, and everything makes sense in the context of relativity. Okay, so it's very cool. So anyways, I just wanted to show you that because I think this idea of this center of momentum frame is an important one in general to be aware of, and this concept of available energy. When you move to an inertial reference frame in which the total momentum is 0, then the kinetic energy is minimum, and all of that energy is available. That particular minimum value is what's available to be converted into other forms of energy, like thermal energy, or in more exotic cases, new particles, new rest mass energy, and all that kind of stuff. Yeah. Okay, super. So that's kind of a little bit of a discussion about collisions in one dimension. We derived two general formulas, conservation of momentum, conservation of energy, but then that's not enough to solve the problem. We need to give a third condition, and we consider two examples of that, two very common special cases, important special cases, and that is perfectly elastic and perfectly inelastic collisions. And then this was sort of the end of our perfectly inelastic collision discussion, which talked about things like center of momentum frame and available energy. Super important concepts. There's all kinds of beautiful things to talk about in physics, but okay, enough.